Welcome to OpenStack Networking and PLUMgrid Open Networking Suite for OpenStack. In this video, we're going to cover a brief overview of the OpenStack architecture. We're going to then dive deep into OpenStack networking, its features and components. Last, we're going to look at the role played by PLUMgrid ONS within OpenStack networking. OpenStack is the fastest growing open source community in the world. We see its adoption across hundreds of countries, and more interestingly, across a variety of verticals and use cases. Behind this adoption is the deep need for infrastructure transformation, the ability to deliver services rapidly and on demand, translates into new requirements for the physical infrastructure. At the core of this transformation, and at the core of each and every cloud, sits the network. The network is responsible for providing both connectivity among different resources, such as compute and storage, as well as to ensure isolation across workloads, tenants, users, and applications. When designing a cloud infrastructure, it's imperative that the right network architecture is selected from the start. In this slide, I have summarized a few important metrics to consider when selecting different options. Performance, scale, high availability, and extensibility all play a fundamental role in enabling growth and extension of a cloud offering. Let's now go into OpenStack architecture. OpenStack was designed to control a large pool of compute, storage, and networking resources. All those resources are managed through API and a dashboard. Control is given to both the administrator as well as each and individual user so that they can provision their own resources. When looking at OpenStack, there are 4 core projects that everybody is familiar with. Nova, which takes care of all the compute resources. Cinder, which is responsible for the block storage. Neutron, which is responsible for the network component. And Horizon, which is the dashboard, the user interface to the OpenStack system. OpenStack includes a variety of additional projects. Some of those are also under incubation for the Kilo release. In this slide, it's a graphical representation of the conceptual communication among the different services. The dashboard and the API layer is the main interface to the user. Through this layer, the user can now configure and provision network, compute, and storage resources. Let's now move to OpenStack networking, also known as Neutron. Neutron was introduced with the Folsom release. For some of you that have been familiar with OpenStack in the past, it was previously known as Quantum. Before the existence of Quantum, Nova was the one providing very simple and basic network services. But with more applications and more advanced use cases being built on top of OpenStack, the need for a through network as a service solution became more real. And that's where Neutron came into the picture. Its goal from the get-go has been to provide both operators and tenants with the ability to create rich and complex network topologies and to configure advanced policies. Neutron was built as a technology-agnostic layer with the ability to enable different vendors' solutions. Neutron was also designed for support of advanced services like load balancer as a service, firewall as a service, or VPN as a service. Now let's look at what is Neutron in more details. So first off, Neutron is a REST API layer that enables users to manage the network resources, then enable connectivity between resources that are managed by other OpenStack services. For example, providing network connectivity between virtual machines managed by Nova. Neutron is a fully technology-agnostic framework, meaning that it's built as a plugin architecture, where each and every vendor can expose its solution through the same consistent layer of API, enabling the customer, the end user, to consume different technologies consistently. Neutron was designed to support through multi-tenancy, so the ability to isolate workloads, provide abstractions that are controlled by the tenant, and give full control over the virtual resources to the tenant operator. Through the modular design, Neutron prescribes what the API layer is, but each and every vendor can provide its own implementation, some mapping to a physical network infrastructure, some mapping to a virtual network infrastructure. Let's look at what Neutron provides to the user. The first concept is the concept of tenant networks. You can see a representation of a Neutron network on the right-hand side, as seen through the Horizon dashboard. Tenant networks in Neutron are isolated and need to provide private IP space to each individual tenant, with the ability to be also completely overlapping. It comprises of networks, subnets, and ports. And additionally, where supported, routers. As mentioned earlier, the underlying implementation of each network depends on the vendor selected. So networks can be tagged or untagged, leveraging VLANs, for example, or they can be built using overlay technologies. The second important concept for Neutron is the concept of external networks. Those are not managed by the tenant, they're managed instead by the cloud operator. But those are the constructs that provide for external connectivity to a tenant environment. Now that we understand a little more what Neutron is, let's look at what Neutron is not. There's a lot of confusion around Neutron. Remember, the Neutron is just the front end to the component that then goes and implements the network functionality. As an example, when you select as a Neutron plugin an SDN solution, what happens is that Neutron really is just a pass-through of API call between the user and the backend implementation. So it can be really thin or really thick, depending on the functionality that are available in the underlying infrastructure, or if you choose to go with, for example, the reference implementation of Neutron. In this slide, it's a summary of the Neutron architecture. The Neutron API layer, exposed to the user, and leveraged to create networks, subnets, ports, interfaces, and routers. The Neutron service, which is responsible for talking to the actual implementation of the specific services. You see better in an example where the Neutron service is the one responsible for interacting with the layer 2 agents, the layer 3 agents, the DHCP agents. And then the third layer is the Neutron Plugin API. So that's where the interaction with the underlying plugin happens. In this slide, you also see the service API. That's where the advanced services like VPN, firewall, and load balancer interacts with the basic network functions. Please be aware that some of these advanced services are now being migrated outside of Neutron with its own independent project. The plugin implementation is where the intelligence of the underlying solution sits. And that's where the actual interaction with the backend happens. And as mentioned earlier, the backend can be anything from a virtual network infrastructure to a physical network infrastructure. Last, as shown in this slide, Neutron was designed from the get-go to enable users to benefit from vendors' extensions. What extensions mean is the ability for a vendor to provide a set of functionality that is outside of the core Neutron implementation. So the Neutron plugin, it's written in Python. The key to understand is that unless you select a specific option, which we're going to talk about in a second, there's only one active Neutron plugin at a given time. So what this means is that when you go and set up your OpenStack cloud, leveraging a distribution of your choice, during the installation process, you're going to be asked to select which Neutron implementation you want to leverage. What is important though is that each and every implementation exposes the same consistent set of API through Neutron. The only option to leverage more than one backend implementation is the ML2 plugin, which enables multiple layer 2 plugins to be consumed simultaneously. In this slide, you can see a representation of Neutron when leveraging agents to implement some of the layer 2, layer 3, DHCP, and advanced services features. In case of this implementation, these agents will reside on either network nodes, so dedicated servers that run these components, or as user space components within each compute node. As a reference, you can see in this slide a compute node, and you can see an agent running in the user space. When leveraging this implementation, there are a few key architectural challenges to comprehend. The first one is that when advanced services run on dedicated nodes, there is limited high availability and a very critical performance component. As you can see from this slide, in fact, all VM traffic will have to be punted up to the local agent or all the way to the network node to receive layer 2, layer 3, DHCP, and advanced services. So the placement of the network node becomes extremely critical, where those network nodes are now sitting in the data path and can be very easily become bottlenecks. When scaling the environment, sizing of the network nodes is critical. And VM traffic can be handled differently depending on the different services, either in kernel, user space, or within the network nodes, translating into a very different level of performance. Now let's move to the last section, covering PLUMgrid ONS and its role within OpenStack networking. PLUMgrid Open Networking Suite for OpenStack. It's a software-only solution that provides scalable and feature-rich multi-tenant networks within OpenStack. It's built on top of overlay technologies, hence enabling users to deploy it on top of any existing physical network infrastructure, and provides tenants the constructs of virtual domains, isolated, secured environments with rich features and topologies. PLUMgrid ONS provides a rich portfolio of virtual network functions that are fully distributed within the Linux kernel. It also leverages a service insertion architecture to enable users to consume third-party applications as part of virtual domains. PLUMgrid ONS is integrated and certified with all the major OpenStack distributions, making it extremely simple and painless to select and deploy PLUMgrid as as part of your OpenStack deployment. PLUMgrid ONS is built on an extremely scalable and high-performant architecture. Its high availability and non-stop features make it the best choice for a large-scale deployment. Now let's look at the components of PLUMgrid ONS. There are three major components. The PLUMgrid director, who is the brain of the system. The director is deployed always as a cluster for high availability reason. And that's where the interaction between PLUMgrid and OpenStack happens. When the user defines a tenant network through the OpenStack dashboard or API layer, these will translate at the director level into a PLUMgrid virtual domain. The PLUMgrid directors are responsible for managing an entire PLUMgrid deployment, what we call the PLUMgrid zone. Upon the creation and definition of virtual domains, the features and functionality will then be implemented within the kernel layer inside what is called the PLUMgrid IO Visor. The PLUMgrid IO Visor is a programmable data plane component that sits within each compute node. It's capable of implementing dynamically and extensively all the layer 2 to 4 services that are needed by OpenStack tenants. PLUMgrid IO Visor edges provide the network functionalities to virtual machines. They're interconnected through overlay networks. The last component is the IO Visor gateway. The gateway is the point where the translation between the new overlay network and the old legacy physical network happens. It's also where the connectivity to the external infrastructure, such as the internet, happens. As you can see from this architecture, there is no single point of failure, with the director being implemented as a cluster and each IO Visor being capable to implement the full-fledged feature set in a fully distributed manner. As more servers are added to a cloud deployment, the scalability and performance of the system will just simply grow with it. Now that we understand the PLUMgrid ONS architecture, let's look at how Neutron interacts with it. When deployed with the PLUMgrid plugin, there are no agents in the implementation. So the Neutron server will interact directly with the PLUMgrid director, who will then be responsible to work with the IO Visors to implement all the layer 2 to 4 services in a fully distributed manner. Looking at the compute node representation, the PLUMgrid IO Visor, sitting in the kernel space, is where all the layer 2 to 4 services are. Now let's look at how this changes your design. First of all, the PLUMgrid director is now only responsible for control plane services. So no data traffic will ever be sent to the PLUMgrid director, making its placement and sizing simpler. All the features are now implemented, distributed within the IO Visor kernel module, making the virtual machine to virtual machine traffic flow optimized. Virtual domains and virtual network functions within virtual domains scale out automatically as more servers are deployed, making growing your environment extremely simple. PLUMgrid ONS has been designed from the ground up for mission-critical network services. We hope this video helped you understand the differences between OpenStack Nova, with very simple network functionalities, to OpenStack Neutron, designed to support rich multi-tenant network topologies, all the way to the fully distributed and scalable nature of the PLUMgrid Neutron plugin. Thanks for your attention.